these two organometallic reactions, the Grignard and the Gilman. So everybody just take a second and see if you can't predict me the products of these reactions here. All right, so in both of these reactions here, so first of all, we called these organometallic reactions, right? Because they both feature these metals in our reagents, right? So that's where that name comes from. And both of these reactions create what type of new bond? Between what elements? What and what? Carbon and carbon, right? So that's what makes these reactions both powerful and kind of a pain in the butt from a predicting product standpoint, is that we're going to be creating a new carbon-carbon bond. So we're going to get this big, ugly product on the other side, right? We're going to join these two molecules together. We're not just swapping functional groups, we're actually connecting them. So the first step is we got to figure out which two carbons we're going to be connecting here, right? That's definitely got to be the first thing that we think about when we approach these problems. Okay, so focusing on our Grignard reaction, we're going to be connecting our carbonyl carbon with the carbon at the base of our metal, the magnesium. Those are the two that we need to link up here. All right, so I'm going to draw my 1, 2, 3, 4 carbons from this ketone. All right, 1, 2, 3, 4. And I'll still color that one, because now I need to draw my new carbon-carbon bond. All right, so on the other end here has to be that blue carbon, because that's what I'm linking together. All right, so now I got to include the other parts of that blue fragment. Right, so that was 3 carbons total. I got one of them down, so I need to draw these other 2. Okay, there's something missing from my product here. All right, what's the functional group in our product of a Grignard reaction? An alcohol, right? So this oxygen is missing. It's no longer a carbon-oxygen double bond, but it is a carbon-oxygen single bond or an alcohol group. Right? So for our Grignard reactions, we always have these alcohol products. And then we can always double check by counting carbons. 1, 2, 3, 4. And remember, we should have the same number as the total of our 2 reactants together, right? So 4 from that fragment plus the 3 from this for a total of 7. Gilman, same idea. We got to figure out which 2 carbons we're linking together here. Okay? Again, it's going to be the carbon at the base of my metal. All right, there's no carbonyl group here, but again, it's the carbon at the base of my functional group, that bromine. All right, so the carbon at the base of the bromine, these are the 2 I'm going to connect together. All right. So I'm going to start by drawing these 5 carbons from my alkyl halide with, the fragment with the bromine on there. Boom. I'm going to color that middle carbon green because that's where I'm attaching. And what am I going to do with that double bond? Am I going to keep it? Am I going to turn it into something else? I'm going to keep it. It stays, right? This isn't a reaction of that double bond. We're substituting that bromine, so this stays. Okay? And what we talked about, the one thing that we got to keep in mind with these Gilman reagents is when I attach this fragment here, I have to do it in the same direction in which that bromine's pointing. So it's pointing down on the same side of that methyl group, so I'm going to draw my bond pointed down as well. Right? And just like before, on the other side of this bond is that blue carbon, because that's what I'm linking together. So then to finish this off, I just got to draw those other 1, 2, so there's a total of 3 carbons there. I got 1 down, 2, 3. Okay, and I can go in and count carbons, make sure. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3. 1, 2, 3. Check, check. Okay? So we're creating new carbon-carbon double bonds, so that's our first step, is we got to figure out how to link these two together. All right, now, the next, we're going to sort of build off of these Grignards here, because there's something kind of cool that we can do with these Grignard reactions that combine a lot of our concepts from previous chapters. All right, so first of all, I'm just going to make a short list of reagents that we've studied previously over here, just to kind of have these listed out. Okay, you don't have to write all these down. What you're going to do is you're going to pick from this like word bank here, or this reagent bank. All right, so we got this list of 4 reagents here. Okay. Let's say that I have this alcohol, 1-pentanol. And my goal, not pentanol, what am I thinking? Propanol. And my goal is going to be to turn it into this. Okay? How are we going to go about doing that? So first of all, how many carbons do I have on the left? 3. How many carbons do I have on the right?
Way more.
Way more, yeah. Right? So bottom line is I need to make a new carbon-carbon bond here, right? I need to grow this molecule. Okay, so boom. How do we know how to do that and create an alcohol functional group? Those Grignard reactions. Okay? The problem is that Grignards don't react with alcohols. What type of functional group do they react with? Carbon, what's the fancy little ending, right? What do we call these? Carbonyls, right? I need the carbonyl in order to grow that carbon chain. But if we dig on what we learned last chapter, we know how to turn alcohols into carbonyls, right? So if I can turn this thing into a carbonyl, then I can do a Grignard reaction to get my product. Okay? So, what I want you guys to do is to try to think which one of those reagents from your reagent bank you would use, right? Now we got to remember what the heck we did last unit in this exam. How are we going to turn this, using one of these here, into a carbonyl group? So everybody take a second and see if you can't remember which one of these would work. All right, let's take a vote here. Who thinks it's A? Who thinks it's B? What about C? And then what about D? Okay, so both C and D do these oxidation reactions, right? But D is a strong oxidizer. So if I took an alcohol and I did D, I would get a carboxylic acid. That's not what we need. So what we're going to use is that DMP, that Des-Martin, whatever it was, all right? And that will convert my alcohol into an aldehyde, all right? Convert it into that carbonyl group. So now you guys are going to finish off this reaction here by telling me what my Grignard reagent should look like in order to get to our final product here. And again, the key, how many carbons we got? All right, make sure you have the same number of carbons down here as you have in our final products. All right, how many carbons should be in my Grignard? 3, right? Because I got 3 in this and 6 total. So I have a 3-carbon Grignard here. Okay, and then just to make sure that we can kind of see what's going on here, if I color, whoops, let's say that I color these 3 green and these 3 blue. Which carbons came from my aldehyde here? The green or the blue?
The green.
The green, awesome, right? Because the one that had the double bond now has that carbon-oxygen double bond, now has that carbon-oxygen single bond. Okay, so one of the things that you're gonna practice on your homework is turning a small alcohol into a larger alcohol by first using these oxidation reactions, right, that we learned about last chapter, and then our new Grignard reactions to create that new carbon-carbon bond. Okay. Now, the real topic of this chapter were ethers, and we've barely talked anything about ethers other than to mention that they're the solvents that we carry out those organometallic reactions in, right? So now we're actually, and honestly the reason for that is that ethers are boring as crap as far as functional groups go. They aren't very reactive, they just aren't very, they're just not very reactive of functional groups. They're very rarely the starting point for any sort of an organic synthesis here. All right, so we're gonna learn about 2 reactions of ethers. We'll just cover one of them today, and that is how to create ethers. All right, so ether synthesis. Okay, this method was developed by scientist with the last name Williamson, so we call it a Williamson ether synthesis. Okay. And it actually just uses reactions that we've studied up until this point. So, if we start with an alcohol, and we treat it with sodium hydride, NaH, does anybody remember what the product of this reaction would be? What happens here? Cool. All right, so what we get is just that oxygen, but now with that negative charge. All right, we pluck that hydrogen off. This is that acid-base reaction. All right, and these things here fell under that category of being both a strong base and a strong nucleophile. Since it's a strong nucleophile, I can take this same thing. So in step 2, I'm going to take this, and I'm going to react it with an alkyl halide. All right, and I will tell you that this is an SN2 reaction, so everybody take a second and try to predict me what the product of this reaction would be. All right, so remember my nucleophile is going to react with that electrophile, the carbon at the base of our leaving group, to create this here, which is our ether. All right, so in that previous chapter when we were learning about these substitution and elimination reactions, oftentimes our products were these ethers. We just never really bothered to talk about the fact that we were creating ethers, right? We were very focused on what type of reaction occurred, substitution or elimination, all that jazz. But anyway, we just combined two reactions that we've learned about before, these reactions of alcohols with our reactions with our alkyl halides, our substitution reactions, to create an ether here. Okay, so before we talk a little bit more about this, I'll leave this up here, but I just want you all to take a minute and predict me the product of this reaction here. So what this is going to look like is first, I'm going to hit this thing with the sodium hydride, and then I'm going to follow that up with this alkyl halide here. Is not 2. Okay. That clock is busted. Good to know. All right, so that first step creates that oxygen with the negative charge, which is our nucleophile, and that attacks our electrophile here, right? So there is that carbon, so boom. Okay, and again, we've created an ether, right? That's the whole shtick here, is we're trying to make ethers. So two reactions we've studied previously combined together can turn an alcohol and an alkyl halide, right? This is an alcohol. This is an alkyl halide. into an ether. All right. Cool. So the real challenge, so that's all well and good. The real challenge of these reactions here is I'm going to give you an ether. And you're going to have to tell me what two things to mix together, right? And there's going to be one important consideration that we have when we're doing this. So I'm just going to give you an ether here. And we want to figure out what alcohol and what alkyl halide we need to combine together to get this particular product. All right, that's going to be the name of the game here. So real quick, let's take a step back and look at our previous reaction that we just talked about, right? Notice that if I split this thing at the oxygen, one fragment, this orange one here, one side of that came from my alkyl halide, and the other side of that came from my alcohol. Right? So same thing over here. If we take this and we split it at this oxygen, one side is going to be my alcohol, and the other side is going to be my alkyl halide, right? But the question is, like, which is which? Which side is the alcohol? Which side is the alkyl halide? Because in theory, I could have two different options here. I could either make the green chunk the alkyl halide and the blue chunk the alcohol. Just try to be consistent with my coloring here. Or I could do the reverse. I could make the blue chunk. No, I'm sorry. I could make the green chunk my alcohol. And the blue, oh my gosh, sorry. Wrong color. It's Friday, y'all. And the other one, here we go. Ooh. Okay, so this is going to be the tricky part, is like which is which here? Which one of these two combinations are we going to pick? All right, and what we got to remember is that very first step is to treat these alcohols with that sodium hydride, which again turns these in to these strong nucleophile, strong base category here. All right, and then as we said, that in order to react in the way that we want, we need these substitution reactions, right? If it was an elimination reaction, that doesn't help us at all. We would specifically need that substitution reaction to create our ether. So real quick, let's just go back and look at our little cheat sheet that we created 100 times. Okay. Oh, wait, I lied, sorry. This particular one, this is a strong nucleophile, strong base. Which category does this thing fall into? Going back and looking at our chart. This thing here.
So the first one, the strong base, weak nucleophile.
Strong base, weak nucleophile, right? So which one do we want if we want substitution reactions? This thing, or the one on the left, or the one on the right? One on the right, okay? So the bottom line is, for these Williamson ether synthesis, we're going to make sure to choose, in this case it would be this set of reagents up here. Wait, no. Okay, fuck, I messed that up. Okay. Rewind. We have another problem here, which is the alkyl halide itself, okay? Because yes, this is a strong nucleophile, but it's also that strong base, and so we have this tertiary alkyl halide here. And remember, this thing like can't get in there. All right, it's all crowded. So I messed that up. All right, bottom line here is, when we do these reactions here, we need the smaller fragment to be the alkyl halide. That way our nucleophile can come around and hit that electrophile. Right? This was a bad example, because actually this category here, both of these would be, the major product would be an elimination reaction here, okay? But remember, we always have this competition between the two that's going on. So although our major product might be elimination, our minor product would be this substitution reaction, all right? The bottom line is, we need the smaller fragment to be our alkyl halide, and the larger fragment to be our alcohol. Okay, so for these Williamson ether synthesis here, this is what we're going to keep in mind. So not this one. This one here. All right, so we can just say Williamson. We need the larger fragment to be our alcohol, and the smaller fragment to be the alkyl halide. And again, the reason why that's important is because the alkyl halide has that carbon that needs to be attacked, so the smaller fragment is less sterically hindered. Okay, so when we're doing our reverse synthesis here, again, we're going to make the larger part the alcohol, and the smaller part the alkyl halide. Chop at that oxygen. Yeah, larger fragment is the alcohol, smaller fragment is the alkyl halide. All right, and I guess actually to be even more like specific, it's not so much how many carbons there are, it's the more substituted fragment needs to be the alcohol, right? It's all about how crowded that carbon is, and the less substituted is the alkyl halide. All right, I apologize. I kind of botched the delivery on that one. Okay, so let's just practice this. All right, so again, your goal is to tell me, let me just steal this, what the alcohol and the alkyl halide will be to create these two ethers.
In this type of reaction, will the alkyl halide always include the Br?
Yeah, they
Won't be another.
in theory, it doesn't necessarily have to be, but that is bromine tends to be the go-to. It's both cheap and like iodine's better, but it's more expensive. Chlorine's less reactive, but cheaper. Bromine's like that Goldilocks sweet spot area. So bromine is kind of the go-to aldehyde, or halide here.
Okay.
And more importantly, that's what your homework will look for. All right, so I'm going to kind of go through this quick just because, again, I want to give you guys time to view your exams here. I'm going to cut at my oxygen, and my goal is to figure out which side is which, right? And again, it's this idea, this larger fragment is the alcohol, but really we need to look at this carbon here, right? Let's just call these carbons 1 and 2. And we want to ask ourselves which carbon is more substituted, carbon 1 or carbon 2? Carbon 1, right? So that more substituted carbon, that more crowded carbon is going to be my alcohol. And that less crowded carbon is going to be my alkyl halide. All right, so we're going to do the same thing here. And this one I specifically tried to make a little bit trickier.
Are we going to be bringing, for the previous example, we had written oxygen to the negative, but for this one you're writing OH because it's an alcohol?
So remember that the Williamson ether synthesis takes an alcohol and an alkyl halide. It's just that first step. If you write out both of your reagents, your first step is to make it an oxygen with a negative charge. So you start with an alcohol, and then you hit it with this thing here, and that's what gives it that negative charge. So it's always a two-step process if you're doing a Williamson ether synthesis. Okay. So again, let's see. So first of all, the green fragment has more carbons on it, straight up, if we just count carbons. But again, the real key is let's look at the carbon on either side, and we'll number them again, 1 and 2. And we want to ask ourselves, which carbon is more substituted? Right? So how many carbon neighbors does 2 have? It's got 2. How many carbon neighbors does 1 have? It's just 1. All right? So even though the green chunk's bigger, that carbon is actually less crowded. So my blue will be my alcohol, and my green will be my alkyl halide. This and this. Okay, and actually you make a good point. I'm kind of blanking on which one your homework asked for, but let's just be clear. This is what we would call an alcohol, obviously. We learned about that. I guess the other thing that it could ask for is the oxygen with the negative charge. Okay, and we'll be able to tell because it will ask us for what's called an alk oxide ion. All right, when you pull that hydrogen off and give that oxygen a negative charge, it's what's called an alkoxide ion. Okay, so again, so your homework for this weekend will really focus on those organometallic reactions, the Grignard and the Gilman. I don't remember what this homework asked for, if it asked for the alcohol or the alkoxide ion, but I'll check on that and we'll review that next week, because your homework on this won't be until next week. Cool? All right, so let's take a minute to hand back these.